Occasionally, there are very interesting topics in physics that are totally unappreciated. One such thing is mass, which could be colloquially called the amount of stuff something is made of. However, there are lots of interesting facets of this seemingly simple concept. Now, I'm not talking about the origins of mass, for which I've made a video. Watch it, by the way. It's one of my favorites. Or even about the Higgs field and its role in giving mass to point-like subatomic particles. And of course, I've made a couple of videos about that too. No, I'm talking about a very interesting idea that only requires the types of topics one encounters in an introductory physics class in either high school or the first year of university. This isn't about Einstein's theory of relativity or anything like that. You don't even need calculus for this one, just straight algebra. I'm going to start with some basic equations and then tell you what it all means. So this is how it goes. We've all been indoctrinated in the idea that there is only one kind of mass, but it turns out that, conceptually speaking at least, there are really two kinds. One type of mass is the mass that resists motion. Push a marble and it moves extremely easily, whereas if you try to push a car, it's a lot harder. This is tied to the notion of inertia, and therefore it's called inertial mass. Basically, it says that for any force you put on an object of small mass will accelerate a lot, and an object of large mass will accelerate just a little. And for those of you who've taken a physics class, this is just Newton's second law, F equals ma. Now this is where we need to begin to be careful. If the kind of mass we're talking about here is inertial mass, then we actually need to add a subscript to the mass and say F equals m subinertial times a. It's important to note a couple of things. The first is that this has nothing to do with weight. It's equally true in deep space, far from any planet. And the second thing is that it doesn't matter what is the origin of this force. It could be someone pushing it. The force could come from a rocket. The force could come from telekinesis. It doesn't matter. Telekinesis isn't real, by the way, but if it did, it would apply here. There is a second kind of mass, and this mass is tied to both gravity and weight. An object with more mass is simply attracted by gravity more strongly to other masses. Newton's theory of gravity says that the attractive force between two objects with masses m1 and m2 is F equals g, m1, m2, divided by r squared, where g is just a constant and r is the distance between the two objects. But because we're being careful about types of mass, we must call this kind of mass gravitational mass, and we would then write the equation with the subscripts like we see here. So this is the first key point, that there is inertial mass, which resists motion, and there's gravitational mass, which is kind of like the charge of gravity. This seems like a cautious point, but bear with me. So what happens if we try to combine these two ideas? What does it do for us? Well, we could put an object in a gravitational field and see how the object resists changes in motion. That, by the way, is an overly fancy way to say that we could drop a ball and see what happens. Since we have a gravitational force, we can equate that to the equation of Newton's second law, F equals ma, F equals m inertial times a. So writing that out carefully, we see that m inertial of the ball times the ball's acceleration equals g times the gravitational mass of the ball times the Earth's gravitational mass divided by the distance squared the ball is from the center of the Earth. And if we want to solve for the ball's acceleration, we get this equation here. We see that the ball's acceleration depends on some constants times the ratio of the ball's gravitational to inertial mass. Okay, let's leave the math for a moment and ask what experiment tells us. After all, physics is ultimately an experimental science. If an idea disagrees with the measurement, it's wrong. Way back in the day, Aristotle thought that a heavier object would fall more quickly than a lighter one, which we now know isn't true. Legend has it that Galileo dropped two balls, one heavier and one lighter, off the Leaning Tower of Pisa and saw that they fell identically. By the way, that probably didn't happen. He actually experimented with objects rolling down an inclined plane, but his conclusion was valid. In the era of the Apollo lunar landings, astronaut David Scott dropped a hammer and feather at the same time while he was on the moon. Working with BBC, physicist Brian Cox repeated the same experiment here on Earth when he had some feathers and a bowling ball dropped in an enormous vacuum chamber, and the two fell identically. But the bottom line is that the objects of different inertial or gravitational mass fall at identical rates, which means that they experience identical acceleration. And, getting back to our equation, that can only happen if the object's inertial and gravitational mass is the same. Then they cancel out in the equation, and you get the formula that you might have calculated if you ever took physics. So you might be thinking, so what? That Lincoln guy sure took a roundabout way to show me something I already knew. But now, this is the part where it gets very interesting. Remember that inertial mass is what resists motion, and gravitational mass is effectively the charge of gravity. Shouldn't we expect that they cancel? Well, no. What if we did the same exercise, but this time, instead of using Newton's law of gravity, we used Coulomb's law? Coulomb's law describes the force between two objects with electric charge. It can be written as F equals K times Q1, Q2 divided by R squared. In this case, K is a constant and Q means charge. If we ask how an object moves under that force, we would then equate it to the inertial mass times acceleration. If we solve for acceleration, we'd see an equation like we've seen before, but the ratio would be the electric charge of the ball divided by its inertial mass. And we know that those two things don't cancel. After all, charge and any kind of mass are different. But they do cancel for gravity. And this is telling us something incredibly profound about the universe. It is saying that an object's resistance to motion is tied very intimately to an object's gravitational influence. Just why that's true is not really understood. However, Einstein took this idea and said that inertial mass and gravitational mass were identical. Mind you, this was just a hypothesis, although, as we've seen, a reasonable one. Using this hypothesis, one of the consequences is that he could derive his theory of general relativity, and in general relativity, gravity is understood as the bending of space and time. Gravitational waves and black holes at event horizons and clocks slowing down in high gravitational fields, and all that are consequences of the equivalence of inertial and gravitational mass. So this is really pretty amazing, and I'll bet you didn't appreciate its significance. The fact that there's only one kind of mass is deeply tied into the very fabric of the entire universe, and that has just got to blow your mind. I like this video because it shows us how something that is seemingly simple can have deep and unappreciated implications. Who knew? If you like learning about this, let us know in the comments, and of course, we'd appreciate it if you'd like, subscribe, and share. We love reaching an even wider audience. I'll see you next time, and remember, physics is everything.